Hello everyone, welcome to the lecture on uncertainty modeling in AI. And today we are going to look at factor graph and the junction tree algorithm. Of course, I didn't invent any of today's material. A lot of the content on factor graph as well as maximal probability were taken from chapter 4.2 and 4.3 of the unpublished textbook written by Michael Jordan. I also took a lot of the content of the junction tree algorithm from chapter 17 of the same textbook, which can be accessed via the two links over here. I also took a lot of the content on the cluster graph and junction tree algorithm from chapter 10 of the textbook written by Daphne Koller. And I would also encourage every one of you to look at the relevant materials in the textbooks written by David Barber, Kevin Murphy, as well as Christopher Bishop. So hopefully by the end of today's lecture, you'll be able to represent the joint distribution with the factor graph and use it to compute the marginal and conditional probabilities. We'll also look at the differences between a factor graph and the graphical model of that we have looked at earlier, in particular the Bayesian network as well as the Markov random field. And we'll also look at how to use the max product algorithm to find the maximal probability and its configuration given a joint distribution. Finally, we'll look at how to convert a directed graphical model or an undirected graphical model into what we call the junction tree and use it to compute the marginal and conditional probabilities. So far in the previous lectures, we have looked at the definitions of directed graphical models and undirected graphical models, and we saw that these graphical models are actually models that allows us to encode conditional independences in the joint distribution such that we can factorize them into a product of factors over a subset of these random variables. And as a result of this factorization, we'll be able to do the computation of the marginal or conditional probabilities in a much more tractable way. However, we also saw that in the chapter of undirected graphical model that the parameterization or this factorization is not unique given an undirected graphical model. We saw that we can make use of the Hammersley-Clifford theorem as well as the canonical parameterization, and both are correct factorization but in a different form. And today we'll look at how factor graphs can help us resolve this ambiguity by making this decomposition explicit. It will introduce a set of additional nodes for the factors in addition to the nodes representing the random variables to achieve this goal. And unlike the directed graphical models and undirected graphical models, it's important to note that factor graphs are not designed for conditional independences because there's no concept of this separation as well as Markov random field as what we have saw in the directed graphical model and undirected graphical model to help us encode conditional independences. So instead, factor graphs are designed for more explicit details of the factorization. So what this means is that given a factor graph, there's only one way to write the factorization of the product of factors for a joint distribution. Now let's formally define a factor graph. A factor graph is actually a bipartite graph which consists of two sets of unique nodes represented by V and F and a set of undirected edges denoted by E over here. So in the set of nodes that is denoted by V, we will see that each one of these nodes V, it corresponds to a unique random variable in the joint probability distribution from x1 all the way to xn. And the second set of the nodes in the graph, which we denote as F over here, it consists of the set of factors that represents the potentials or conditional probabilities that contains the random variables that is linked to this particular factor in the bipartite graph. And of course, the undirected edges E over here, it links each factor nodes to all the random variable S that this factor depends on. And it's also important to notice that because we define the undirected edge in such a way, we will not see that there is any edges or there won't be any connections between the random variable nodes in between the factor nodes over here. So these edges will only exist in the connection between a factor node as well as the random variable node. We'll use the round nodes to represent the random variable and a square node to represent the factors, following the definition or the notation defined in the textbook by Christopher Bishop. Now, given a factor graph, we can write the joint distribution over a set of random variables in the form of the product of the factors, where here the probability distribution of the random variables represented by x. So this could contain x1 all the way to xn over here, and is equal to the product of all the factors represented by the factor graph that consists of xs, which is a subset of the all the random variables relevant to the factors of fs, and each of these fs is simply a function of the corresponding set of random variable. An example would be a 3-node factor graph over here, where each node represents x1, x2, and x3, for example. And then there's a factor between x1 and x2, which we call f12, and there's another factor between x2 and x3, which we call f23. So there could also be a unary factor, which consists of only the factor random variable of x3, for example, which we denote as f3 over here. So the joint probability distribution of this example, x1, x2, and x3, it would be simply the product of all the factors that are encoded in this particular factor graph. So we can see that there's only one way to write this particular factorization, and that is the only way which is encoded in this factor graph. Or more explicitly, we can see that the function of f12, the potential of the factor of f12 would be a function of x1 and x2, and the function of f23 would be a function of x2 and x3, and finally the factor of f3 would be simply a function of x3. So this means that given this particular graph over here, this particular factor graph over here, there's only one way of factorizing this joint probability distribution, which is given by this equation over here. So another example over here would be also a 3-node graph, which consists of 3 random variables, x1, x2, and x3. So we can define FA to be the factor that links x1 and x2, and FB to be the factor that links x1 and x2 as well as a factor of FC and FD that links x23 and x3 respectively. So we can see that when we are given this particular factor graph, there's no ambiguity of writing the factorization of the joint probability distribution, and there's only one way of doing this, which is following the equation that we have seen earlier on, where the joint probability distribution is simply the product of all the factors fs, and where the factors is a function of all the random variables that it is linked to. And in this particular case here, we can see that the joint probability distribution of fx1, x2, and x3 is simply equals to the factor of fa multiplied by fb multiplied by fc and multiplied by fd, where fa, fb, fc, and fd, they are function of the respective random variables that are joined together by an edge from that particular random variable to the respective factor nodes in the factor graph. And it's interesting to note that there are two factors, fa and fb, that are defined over the same set of random variable. So in this case here, if we were to compare this in a Markov random field or a directed graphical model, there's simply no way to encode this explicit form of factorization which consists of the same random variable. For example, in a Markov random field, if I were to write this here, then simply the only way to write this would be a function, a potential over x1 and x2. We won't do this twice. We won't write this as psi of A, x1, x2, and psi of B, x1, x2, because this form of factorization is simply not read off directly from the Markov random field representation in this case. But it's interesting to see that in factor graphs, we can actually represent this factorization between FA and FB, which contains the same set of random variables x1 and x2 explicitly. And similarly, for FC and FD, it could be also combined into a single potential over x2 and x3 in the case of the Markov random field. So in this case here, we will simply write in the case of a Markov random field x2 and x3 over here. We'll simply lump all this together into the potential of x2 and x3, where there could also be a unary potential of x3, but this is not explicitly encoded in this Markov random field, as we have seen in our earlier lecture on the parameterization of a Markov random field. But in this case here, when we are given this particular factor graph, the factors of FC and FD are explicitly encoded in this factor graph. What this means is that there is only one way of writing this factorization of the joint probability distribution, and it must contain FC and FD respectively. So in other words, the factor graph actually keeps such factors explicit, so it's able to convey more detailed information of the underlying factorization. But one interesting thing to see here is that there's no concept of Markov property, as well as there's no concept of deseparation that would allow us to read off any form of conditional independences from the factor graph. And let's now look at how to convert a directed graphical model to a factor graph. So recall that the factorization of a directed graphical model is defined by the parent-child relation. So in the case here where we have a joint probability distribution of x1 all the way to xn, this is equal to the product of all the random variable, each respective random variable of xi, conditioned upon the set of the parent nodes. So xi over here would be there would be arrows pointing towards xi, and these nodes are collectively known as the parents of xi. This is what we have seen in the earlier lecture of undirected graphical model. Now, given the factorization from the parent-child relationship of a directed graphical model, we can directly convert a directed graphical model into a factor graph by simply representing the local conditional probability distribution given by the parent-child relation as the factors of fs, xs, where fs, xs over here is simply the same as the local conditional distributions given by the parent-child relation, and xs here would be simply the set of the node as well as all its parent nodes, and the factor of fs would be simply the conditional probability of xi conditioned upon pi I. And plugging this particular equation back here by substituting this guy with the parent-child relation, we can see that we will arrive at the same factorization given by the factor graph as defined earlier on, where this is simply the pi of f, fs, and xs over here. So we can also convert an undirected graphical model to a factor graph. Recall that the factorization of an undirected graphical model is given by this form over here, where z over here is the partition function. It's the partition function that enables us to normalize the potentials into a valid probability distribution. And y over here are all the random variables, say for example y1 all the way to yn over here. So notice that there's no particular reason on why I represent this random variable as y, and why I represent this random variable in the directed graphical model as x. This is simply because I'm following the different textbooks or different materials on the definitions over here, but they are essentially the same thing. And phi or c over here simply represents the click potentials that consists of all the random variables yc in the click, or in the maximal click, if we are following the Hammersley-Clifford theorem. And we can convert the undirected graphical model into a factor graph by simply representing the potential functions over the maximal clicks as the factors. So in other words, we will simply let phi of c yc over a certain click, over a certain maximal click of c to be representing a factor of fs, and all the random variable inside here would be simply the random variable inside here. So to be more specific, or to be consistent with the notation, I think we should represent this as ys over here. So what it means over here is that within the factor of fs, that corresponds to the potential, the click potential, or given by size c over here, all the random variables inside here should be yc, which is all the random variables that is contained in this maximal click potential function. And if we were to rewrite this and plug it back into this equation over here, we can see that this would simply turn into the factor graph definition, the factorization definition of a factor graph of product over S and F S Y S over here, where it's important to note that since the partition function is also a factor, can be considered as a factor over here, but is independent of any random variable, we can define this 1 over z over here, the partition function over here, as a factor that is defined over an empty set of random variables. So this could be also incorporated into fs over here, where in this case y of s that corresponds to 1 over z here would be equals to a null set. It is also important to note that there may be several different factor graphs that corresponds to the same directed graphical model or undirected graphical model. So this means that given a undirected graphical model or a directed graphical model, the conversion to a factor graph is not unique. Is not unique. But what's interesting here is that after we have converted a directed graphical model or undirected graphical model into a factor graph, the factorization of the joint distribution becomes fixed. There's one only way to factorize, to do the factorization of the joint probability distribution given that particular factor graph. An example here of a directed graphical model is this V-shaped structure over here, which consists of 3 random variables, x1, x2, and x3. So with x1 pointing towards x3 and x2 pointing towards x3. From the parent-child relation, the joint probability distribution of x1, x2, and x3 would be given by the prior probability distribution of x1, x2, as well as the conditional probability distribution of x3 conditioned upon x1 and x2 over here. We'll see that there are different ways of converting this directed graphical model into a factor graph. So one of the way to do it would be given by this factor graph over here, where we simply lump all the random variables together into one particular factor of x1, x2, and x3 over here. And this would simply, this particular factor here, we can simply write it as the joint probability distribution, or the factorized joint probability distribution that we've seen in the original directed graph. So what this means is that we didn't there's no need to explicitly state that this particular fact can be further factorized into Px1, Px2, and P of x3 conditional upon x1 and x2. We'll simply write all this together into one factor that is given by the factor of x1, x2, and x3. So, but what it means here is that when we are given this particular form of the factor graph, then there is only one way of writing this joint probability distribution, and that has to be given by the factor of x1, x2, and x3 together. We don't really care about this particular factor can be further factorized, or rather there won't be a notion of the further factorization that is encoded in this particular form of the factor graph. There is also another way which we'll see on how to represent this directed graph as a factor graph given by this diagram. We can see that in this case here, we can also explicitly denote that there is a factor over the random variable of x1, as well as there's also a unary factor over the random variable of x2. And similar with the previous example, we can also denote a factor over all the three random variables of x1, x2, and x3. So in this case, given this particular factor graph, there's only one way to write this factorization, and that would be given by FA. So the joint probability distribution here, x1, x2, and x3, would be given by the product of FA multiplied by FB and FC. So in this case here, the factors has to be explicitly factorized into this form as represented by this particular factor graph. See that FA is corresponds to the marginal probability distribution of x1, and FB corresponds to the marginal probability of x2, as well as FC corresponds to the conditional probability of x3 conditional upon x2 and x1. And here in this case, we'll see that this factor graph encodes the explicit factorization of these three terms into FA, FB, and FC. Whereas in this case here, we don't care about the further factorization, because given this particular factor graph, there is only one way to write the factorization, which is the term of F, which consists of x1, x2, and x3. And in order to represent the same joint probability distribution, we need to write this collectively as one factor. And it's interesting to also note that in this case here, we can see that in a directed graphical model over here, due to the d-separation principle, we know that if we are not given x3 over here for this V-shaped structure, if we are not given x3 over here, x1 would be conditionally independent, or it will be independent of x2 given that we don't observe anything. And if in the case that we observe x3, then x1 would not be independent of x2 given that we have observed x3. These are the conditional independences that we can directly read off from this directed graph over here. But we can see that in the factor graphs over here, since there's no concept of d-separation, neither is there a concept of Markov property, we cannot read off the conditional independences from the factor graph over here, even though we have converted the directed graph into a factor graph. And this means that the conditional independences are lost in the conversion. Another example would be a conversion of an undirected graph into a factor graph. Suppose that we are given these three nodes over here, where it's a maximal clique where each one of the pairs of the nodes are linked to each other. And in this case here, we can write the potential following the Hammersley-Clifford theorem, that the joint probability distribution over here over x1, x2, and x3 over here can be simply given by the potential of x1, x2, and x3 over here. And now we'll see that this undirected graphical model can be converted into a factor graph by simply lumping all this particular single clique potential, all the random variables, into a single factor, where this x1, x2, and x3 would be simply assigned the clique potential of x1, x2, and x3 given by the undirected graph. Another way of doing this would be in this case over here, where we say that there is a potential, there's a factor of FA that consists of the three random variable x1, x2, and x3, as well as there's also a factor of fb that consists of x2 and x3 over here. And in this case, sorry, this guy over here should be x3. There's a mistake over here. And here, since we are saying that there's a explicit representation where these two guys over here can be factorized into fa and fb respectively, what it also means that given this particular form of factor graph, we are also explicitly saying that the potential over here, despite that it's represented as one particular term over here, it can be actually explicitly factorized into two different terms over here. So an example over here would be, let's suppose that this guy over here, the potential of x1, x2, and x3 over here, it's actually a polynomial function. For example, this guy over here would be x1 plus x2 plus x3 square, for example, and then multiply by x3 plus x2, for example. So after evaluating this term out, then what we are saying here is that we are representing this polynomial function using to let it represent this particular potential function over here, which in turn represents the joint probability distribution over here. So in the first case of the factor graph over here, we will say that we simply do not care that this guy over here can be further factorized into this form over here. We'll simply write this as x1 multiplied by x2 plus x1 multiplied by x3 plus x2 multiplied by x2 plus x2 multiplied by x3 plus x3 multiplied by x3 square, which is x cubed, plus x3 square multiplied by x2. So this whole term over here is actually, after we have evaluated this product term of the two polynomial functions over here, and we simply collectively call this the potential x1, x2, and x3, as well as the factor of x1, x2, and x3 as represented by the undirected graphical model, as well as this factor graph over here. But in the case when we have explicitly encoded this or convert the undirected graph into this form over here, where we say that there is actually two factors, the joint probability distribution over x1, x2, and x3 over here, it's explicitly factorized into fa and fb, where fa is it consists of it's a function over x1, x2, and x3, and fb is a function of x2 and x3. Then what it means here is that we must be able to factorize this probability distribution here into two polynomial functions, which consists of the first one consists of the x1, x2, and x3, and the second term over here, fb, must correspond to x2 and x3. Now we'll see that an important application of the factor graph is an alternative representation for the sum product algorithm of tree-like graphs. More importantly, we have seen in the earlier lecture that sum product algorithm could not be used in this directed graphical models or undirected graphical models that contains the local cycle. But we will see in this slide that after applying a factor graph onto the this directed graphical model or undirected graphical model with local cycle, we can actually convert it into a tree-like graph or tree-like factor graphs. So here is an example where we turn local cycles into a tree. For example, in this case here, the three random variables, a three-node directed graphical model in this case, which consists of x1, x2, and x3, and the conversion of this into a factor graph, we can see that it can be collectively done by a factor that consists of x1, x2, and x3 over here. So in this case over here, this simply would be represented as the prior distribution of the x1 multiplied by x2 condition upon x1 and multiplied by x3 condition upon x1 and x2, which is simply the joint probability distribution of this directed graphical model over x1, x2, and x3. And here's another example where we convert an undirected graphical model with local cycle into a tree-like factor graph, where we simply represent the click potential over x1, x2, and x3 over here as a single factor over x1, x2, and x3 in the factor graph. So in these two cases over here, we can see that we can turn local cycles regardless of whether it is from a directed graphical model or an undirected graphical model into a tree-like graphs. So here's another example where we saw that in the earlier lecture that given a poly trees, which is defined to be any tree where the child can contain two or more parents over here, and we saw that there will be a lot of local cycles appearing after we have done moralization to convert the directed graphical model of the poly trees into an undirected graphical model. But here we can apply the factor graph conversion from this undirected graphical model that represents the poly tree with local cycles into a factor graph which will become a tree structure over here, where we simply lump all these click potentials together into one particular potentials over here, and this becomes a tree structure which we can see that we can still perform the same sum of product algorithm for inference. So here, given a factor graph, the sum product algorithm, the goal would be to compute all the singleton marginal probabilities under the factorized representation of the joint probability distribution. So what this means is that given a factorized form of all the joint probability distributions, x n, for example, n distribution, and given this factor graph of s, fs and xs over here, what we want to do here would be to make use of this form of representation to get all the possible marginal probabilities of x1, x2, all the way to xn, for example, or even the conditional probability, as we have seen in the earlier definition of the sum product algorithm. And similar to what we have seen earlier in the sum product algorithm, where we have to define some form of message for the message passing, we'll also define two kinds of messages for the sum product algorithm or message passing in the factor graph. So the first type of message which we define to the as v over here would be the message that flows from a variable to a node factor. So here is a variable, for example xi over here, that is linked to a node factor of fs over here. V, the message v over here, would be a message that is passed from the random variable of xi into the factor nodes of fs over here. So this guy over here would be v. And we'll also define a second type of message which we call mu over here. This would be the message that flows from the factor to the random variable node over here. So for example, I have a factor of fs, and this is linked to a random variable of xj over here. And here, in this case, the message would be flowing from fs to xj over here, which we define as mu in this case. So before we can explicitly write down the sum product algorithm for the factor graph, we need to further define two terms. The first term would be n of s in the set of the random variable nodes, which is defined as the set of neighbors of the factor nodes s in the factor nodes. So n of s here is referred to the indices of all the random variable referenced by the factor of fs. So what this means is that given a factor node of fs, n of s is defined as all the random variable nodes. So all the random variable nodes over here that is directly connected to this fs over here. So these guys over here, for example, in this case here, x1, x2, x3, and x4 in this case here. When I say that n of s, what this means is that we are actually referring to the set of nodes x1, x2, x3, and x4 that is directly connected to the factor node of fs in this example here. Another definition that we need to make would be ni over here. This is defined as the set of neighbors of a variable node which is in the set of all the random variable nodes of V. An example here would be, given a random variable node which we call xi over here, ni would refer to all the factor nodes that are directly connected to the random variable of xi over here. So for example, if this case here is f1, f2, f3 and f4, then ni would simply be equals to the set of f1, f2, f3 and f4 in this example over here. Now after seeing the definitions, we're ready to define the messages from the random variable to the factor nodes, which we denote as vis bracket xi over here. So this message over here, it denotes the flow from a random variable node of xi to the factor nodes of fs that are in the neighborhood of xi, represented by ni that we have seen in the previous slide here. So in this case here, graphically, this means that given a random variable of xi, I'm going to compute a message that is from this random variable, that flows from this random variable of xi into the factor nodes of fs over here, which I denote as vis bracket xi over here. So in this case here, it's important to note that a message that flows from a random variable to a factor node, we are not going to marginalize away any of the random variable. This is because this fs here, it has to be also a function of xi. This means that since it is directly connected to the random variable of xi, it could also consist of other random variables if it is connected to other random variables. So what this means is that this fs could be also a function of other random variables. But what's important here in this case here that we look locally here is that the random variable of xi must be contained in the factor of fs over here. And so to compute this message over here, it would be simply given by the product of all the messages that is flowing from the other factors into this random variable nodes of xi, and excluding the message from fs to xi, because now we are computing this particular message from the random variable nodes of xi into the factor node of fs. So the message from I to s would be simply given by the product of all the messages from the factor nodes, from all the neighboring factor nodes, including fs itself, and into the factor node of fs.